Every operations manager lives with a dangerous paradox. Inventory is simultaneously an operation's greatest financial liability and its most essential mechanism for survival. Physical goods, raw materials, work-in-progress components, and finished products represent the most common understanding of inventory. Operations management defines inventory as any stored resource. Beyond physical stock, it encompasses queues and digital information. A queue of hospital patients is a form of inventory. Unprocessed credit card applications in a database represent the same stored value waiting to be transformed. The governing principle is a balancing act. An operation must provide sufficient resources to meet market demand while minimizing the total cost of maintaining those resources. Focusing strictly on physical boxes blinds a manager to the hidden operational queues and data bottlenecks that can choke an entire system. Storing resources burns capital. This is known as the holding cost. Holding costs encompass the opportunity cost of tied-up cash, physical warehouse rent, insurance premiums, and the risk that a product will spoil or become obsolete before it is used. The opposing force is the shortage cost, along with ordering costs. This represents the financial penalty of running out of stock when demand exists. A single missing component can halt a manufacturing line, trigger expedited shipping fees to rush a replacement, and erode customer loyalty. These two cost categories are locked in a strict inverse mathematical relationship. Reducing holding costs by keeping less stock on hand increases the statistical probability of a shortage. Inventory management is a strict mathematical optimization. The goal is to find the exact point of lowest total financial impact. This is the economic order quantity, or EOQ model. It is the foundational equation used to determine the exact quantity of stock to order in a single batch. When you increase the volume of an order, the administrative and setup cost per individual item drops. Bulk orders reduce the frequency of fixed ordering expenses. Simultaneously, bringing in those larger quantities increases the cost to store and maintain them. Summing these two lines creates a U-shaped total cost curve. The point where holding costs exactly equal ordering costs is the mathematical minimum of the curve. The EOQ provides a theoretical perfect batch size, but its validity relies on a fragile assumption that customer demand and supplier delivery times remain perfectly constant. Knowing how much to order is secondary to knowing when to place the order to avoid hitting zero stock. This is the reorder level, or ROL. The baseline calculation is the average daily usage multiplied by lead time. Lead time is the unavoidable delay between placing an order and the goods arriving at the facility. In practice, demand spikes unexpectedly, and suppliers miss deadlines, breaking the assumption of constant variables. To absorb this volatility, managers hold safety stock. This is a statistical buffer held in reserve to prevent stockouts during demand surges or supply delays. Without calculating an accurate reorder level and integrating safety stock, the optimized EOQ batch will arrive too late, rendering the initial math useless. No manager has the administrative resources to monitor thousands of unique items with equal mathematical rigor. ABC analysis is an inventory classification system rooted in the Pareto principle, or the 80-20 rule. A items make up only 10 to 20% of physical volume, but they account for 80% of the total capital value. Because the financial stakes are high, A items require a continuous review system, using live algorithms to trigger orders the moment the reorder level is breached. C items are massive volume consumables, like nuts and bolts, that account for only 5% of the operation's total value. These require only a periodic review. Checking stock levels on a fixed calendar schedule saves significant administrative labor. Treating all inventory with equal intensity misallocates labor toward low-stakes items while leaving high-value assets undermanaged. If EOQ and ROL models are mathematically sound, why do massive supply chains still suffer from sudden, catastrophic shortages? This is the bullwhip effect. A tiny fluctuation in retail demand is amplified into massive variability further up the supply chain. When each node in the chain orders an isolated EOQ batches and adds its own safety stock, they distort the demand signal for everyone upstream. A mathematically optimized warehouse can inadvertently trigger systemic failure for its suppliers if consumption data isn't shared across the network. The volatile operating environment of Southern Africa serves as the ultimate stress test for these models. Port congestion and inconsistent road networks create unpredictable import delays, which invalidates the assumption of a constant lead time. Localized power outages, load shedding, can blind the IT tracking systems required to execute a continuous review strategy. Consider a pharmaceutical distributor handling critical imported vaccines under these conditions. These vaccines are A items. Temperature-sensitive storage increases hourly holding costs, but the risk of patient harm forces managers to carry large safety stocks regardless of expense. When the grid fails, warehouses must rely on diesel generators. This significantly increases the cost of maintaining that safety buffer for every hour the power is out. Theoretical operations math serves as the baseline, but the model only survives when it is dynamically adjusted to account for systemic risk and real-world volatility.